Hey guys, welcome back to the last video for chapter 11. In this video, we're going to talk a little bit more about osmosis and how this might look in a real world setting. So I proposed this idea at the beginning of the class as to why we can't drink seawater to survive. And the reason has to do with osmosis. So drinking seawater to survive. What happens if we drink seawater to survive is the solution inside of our gut becomes a very concentrated solution. So we're ingesting water, we're ingesting sodium chloride, and all kinds of stuff. So we have a very high concentration inside of our gut, and our body cells would have a much lower concentration of solute particles. So we would see the direction of flow of the water would be from our cells inside of our body into the gut to try to dilute that concentration. So we'd actually be taking water, what little water we have in our cells, putting it into our intestinal system and then excreting that water out. So not only are we not helping the situation, we're actually expediting that dehydration process because it's pulling water from our body cells. So drinking seawater actually expedites dehydration in this kind of dramatic situation setting. So let's take a look at different types of solutions and talking about just some terminology that has to do with how do we know if it's going to flow into the cell, out of the cell, which way is it going to flow. So in kind of a perfect world, well, first let me talk about this. We are going to talk about red blood cells. So a red blood cell, kind of in a perfect world, would be this kind of nice, puffy, round cell. It's got a little indentation in the middle of it. Okay? So in a perfect world, in a healthy system, we would find an isoosmotic solution. So the osmotic pressure of the solution inside of the cell is the same as the osmotic pressure on the outside of the cell, so no net flow in or out. It kind of stays put, stays where it belongs. Okay, so that's isoosmotic, the same on both sides. Just another example, same idea. In a hyperosmotic situation, the solution on the outside has a higher concentration of solute particles than the solution on the inside. So high concentration on the outside, low concentration on the inside. So osmosis tells us that the solvent is going to flow to higher concentration. So we're going to see a net flow of water out of this cell. Okay? The reason for that is the osmotic pressure on the outside is lower. There's nothing kind of pushing against or holding back that water. So that water is going to come rushing out of that cell into the surrounding area. This is an example of what would happen when we drink seawater, right? So it would be much more concentrated outside, and so that water would come rushing out of the cell. And what happens if we're talking about red blood cells in this case? Is those red blood cells will end up like shriveling up and being deformed, not having that puffy, pillowy look to it, and then, shrunk, deformed red blood cell is not going to perform the same functions or as efficiently of a function as a big, puffy, pillow red blood cell. Now let's look at the other, so hypoosmotic. In a hyposmotic solution, the outside of the cell has a lower concentration than the inside of the cell. So inside is very concentrated with solute particles, outside is less concentrated. So what we would see here is we would see the flow of solvent would be into the cell. There's higher pressure on the outside and it's going to push its way into the cell. There's nothing in the cell that's holding that water back from coming in. So we'd see a net flow of solvent into the cell. What happens here is those cells get really big and puffy, they swell up, and eventually they can burst, right? So not only are we causing the red blood cell to be disformed, but now it's bursting and is dying, right? So it doesn't have a function anymore. Now, for red blood cells, this isn't really ideal, but this would be ideal for other types of cells that maybe don't have the same type of cell wall. So this is ideal for plants, right? So plants have a very rigid cell wall. So as the water flows into that cell, they kind of perk up a little bit, right? The cells get really full, squishy, and that's when we water our plants and we see them kind of come to life. But as those plants start to lose water, start to dehydrate, we see those cells start to shrivel up a little bit, get a little bit wilty, right? And so we put a little bit of water, we see the water goes into the cell, and those plants perk or puff right back up. So while for red blood cells, this may not be an ideal situation, it could be ideal for something else, like a plant, right? So going back to that first slide that I depicted in this video, so this isoosmotic situation is kind of the best situation, the ideal situation. This one right here would be an example of a hyperosmotic situation where water is flowing out of the cell and it's shriveling up. And then this would be an example of a hyposmotic situation where the water is flowing into the cell, causing them to swell and possibly even burst. So just some terminology associated with osmotic pressure. That is the end of the information for this chapter. I hope you guys found this helpful.